Hi guys, this is EasyElimu channel. I'm Vincent Kanumai and I will be taking you through Form 4 Mathematics. And today we are going to start with the matrix and transformation. Stay tuned as I welcome you all.
Matrix of a transformation. Now, we shall look at triangle ABC. Triangle ABC with the vertices A as 5, 6, B 5, 2, and C to be 2, 2. Let's say you have been given this triangle and you have been told it is transformed through matrix of a transformation 0, -1, and 1, 0. If you subject this triangle to this matrix, you will find a certain image. Let's see what kind of transformation is this matrix representing. So 0, -1, 1, 0. You pre-multiply it with the given triangle or any given figure, you will get a certain image and it will tell you the type and the kind of matrix of transformation you are using. For instance, here is our triangle ABC with these vertices being subjected to a transformation of 0, -1, 1, 0. When you pre-multiply it with this, you get the images as -6, -2, -2, and this one is 5, 2, 2. 5. This is A prime, B prime, and C prime. So we have found that if triangle ABC with these vertices is subjected to a transformation of this one, we get the image of that triangle to be -6, 5, -2, 5, and -2, 2. Let's see on a Cartesian plane how does this image and the object of this triangle looks like. And on plotting the images, this is the A, B, C. On plotting the image of the triangle ABC, that's A prime, B prime, and C prime, we shall get the object being as that one. So, as you can see, we can notice that this object is still the same size as the other image shape. But the only thing that has changed is the figure in which the manner it looks here and here. And we can see that on pre-multiplying it with a translation of 0, -1, 1, 0, it has been changed to this kind of image. So let's see what kind of transformation is this. So any kind of transformation, if you are pre-multiplying a matrix by any 2 by 2 matrix, you will find that all of them originate from the origin or passes through the origin. For instance, this is our origin where it is 0, 0. And if you want to find which kind of matrix is that, then you have to join the two lines using that is form 2 work Like this one, you construct a perpendicular bisector to it. And also, for example, here B, you construct a perpendicular bisector. You join B to B, and you also construct perpendicular bisector to it using your pair of compasses and ruler. And you will find that they both coincide at the origin, that is the center. And on this point, if you want to see which kind of transformation is that, you can see here that this one has been mapped to this one. So meaning, if you take this point from here to here, you can see that this is a perpendicular of that one. So meaning this one has been transformed from ABC to another triangle of A prime, B prime, C prime through a positive quarter turn going the other direction. That is positive quarter turn because it's positive 90 degrees at the origin. And with that we can say that we have found the matrix of a transformation to be this matrix. It will be a positive quarter turn matrix. Any object being transformed with this kind of matrix, it will undergo a positive or a rotation of positive quarter turn, which is positive 90 degrees from the first quadrant to the second. Now, I can say that if you have been given any kind of matrix or any kind of transformation, if you want to know what kind of matrix is that or what kind of transformation is it, you take any object, and in precisely we always take a 1 unit square and we multiply it using this kind of transformation or any given kind of transformation. For instance, here we had this one and we have seen how it works. It will always work to the other transformation you are being subjected to. I will be taking you through the second subtopic, that is finding a matrix of transformation. And here, finding a matrix of transformation, you will be given an object and also an image, and you will be asked in which kind of transformation did this object pass in order to give this kind of image. For instance, having given triangle, let's say triangle ABC, with a matrix or a positional vectors of 1, 4, 1, 1, and 3, 1 as the values of A, B, and C. And here the image of that triangle to be A, B, C, A prime, B prime, C prime to be having negative 1, 4, negative 1, 1, and negative 3, 1. Yeah, as negative 3, 1, that's the value of C prime. So you will be told, find the matrix of transformation for a triangle ABC that turn from this object to this image. First, we need to decide the kind of our transformation that this underwent. And we can say, let our transformation T take the coordinates or the matrix A, B, C, and D. This is our matrix of transformation. And we know from our first session that if you take any kind of transformation, you pre-multiply it with a given figure or a given quadrilateral triangle, it will give you a given image. For instance, here we have been given the object of that triangle, and here the vertices of the image of that triangle. So meaning that if we take our transformation as A, B, C, D, we pre-multiply it with this given object, we shall get our image. Let's see. If we take A, B, C, D, we pre-multiply it with 1, 4, 1, 1, 3, 1 as the vertices of A, B, and C. We shall get the vertices of A prime, negative 1, 4, and that of B prime, negative 1, 1, and C prime as negative 3, 1. Now, we need to find what is the value of A, what is the value of B, and what is the value of C, and also the value of D. And from here we know to get this value here, we have to take the row multiplied by the column of this matrix. And we shall be having this. For instance, A multiplied by 1, we shall get A plus this one, which is 4B. Now it will be A plus 4B, it will give you A 4B, it will give you what? Negative 1. And to get the value of this one, now it will be this, the denominator. Now we are dealing with the denominator, the downward vertex. That is C multiplied by 1 plus 4 multiplied by D. That is C plus 4D is equal to 4. And again, if we want to find the value of B prime, we shall get A multiplied by 1 plus B multiplied by 1, and we shall get negative 1, meaning that our A plus B is equal to negative 1. And again, if we need this one, it will be now this one C multiplied by 1 plus D multiplied by 1, and we get that is C plus D is equal to what? To 1. Together can be done to final one, which is A multiplied by 3 plus B multiplied by 1. That is 3A plus B is equal to negative 3. The remaining will be C by 3, D by 1, and you get 3C plus D is equal to positive 1. Now we need to find the value of the individual components of A, B, and C together with D. Let's see. We now collect the like terms here. For example, we can take A plus 4B because this has A, B, this one has, we take them together and we solve them simultaneously. For instance, A plus 4B is equal to negative 1, and we also take either A plus B equals to negative 1, or we can also take 3A plus 4 plus B equals to negative 3 together with this or the other. Any should work. So if we take this one and we solve it simultaneously, we shall find that here to eliminate this A, we need to subtract. Now, to find the value of now either B or A, we need to subtract to eliminate A. And on elimination, we shall find that if you take 4B minus B, you will get 3B. And negative 1 minus 1 is equal to 0, because this is negative 1, minus becomes positive, and it will be 0. So meaning that our 3B is equal to 0. The value of B now will be, you divide both sides. Now 3B equals to 0, meaning that B, it will be, you divide both sides by 3 to get the value of B as 0. If the value of B is 0, then if you substitute, you take one of the equation, either this equation or the other. You find for the value of A. Now let's see what's the value of A. For instance, that is A plus 4, but B, what is our B? B equals to 0. So only 4 times 0 equals to negative 1. If you multiply 4 by 0, you will get 0, and A will be equal to -1. Now we have found our value of A being -1 and B equals to 0. We can still go ahead and find the value of C and D. For instance, if we want to prove this one is right, we took this, and here we still have that one. So meaning that if we take 3A plus B should give us -3. And A here we have -1. So it is 3 multiplied by -1 plus B, which is 0, and that one gives you -3. So meaning that method was right. Now let's find the value of C and the value of D. In instance, here we have C plus 4D. Here we have C plus D equals to 1. And here it is 3C plus D is equal to 1. Now we can take either this and this, or this and this, or the other way round. Any do work. For instance, let's take C plus 4D equals to 4. C plus 4D equals to 4. And also take C plus D equals to 1. C plus D equals to 1. We can still solve this one simultaneously to find the value of C and D. Now, let's subtract to eliminate C. If you eliminate this one, it will be 0 plus 4D minus D, you will get 3D. And 4 minus 1, it is equal to 3. Now, we have 3D equals to 3. If we need the value of D, we need to divide both sides by 3 to get D equals to, this one cancels with the other 3. 3 by 3, you get 1. So, our D equals to 1. We have found our value of D equal to 1. So if we need the value of C, we now take any of the equation, we substitute D equals to 1, and it will give us the value of C. For instance, let's now take C plus D equals to 1. Now if we take C plus D equals to 1, and we substitute the place of D with 1, we get that C plus 1 equals to 1, implying that C equals to 1, this one, the other side, this one, if it goes the other side, it will be -1, and we get our C equals to 0. Now we have found the value of D, and we have found the value of C. So meaning that if we took these values, we substitute it into this equation, because we use this and this, it should give us 1. For instance, C equals to 0. Take 0 multiplied by 3, you get 0. Plus D, our D equals to 1. D equals to 1. D, 0 plus 1 is equal to 1, meaning our equation are okay. So, we have found the value of A equals to -1, B is equal to 0, C is equals to 0, and D is equals to 1. Now we can conclude that our transformation A, B, C, D, it is these values. Now our T becomes, we substitute the values of A, B, C, and D in this matrix, and we find it will be A equals to -1, B 0, C 0, and D 1. This is our transformation. And if we need to know the type and kind of transformation, you can use the first procedure I used to identify by drawing a Cartesian plane. Now, this image, the object and the image, you will find what kind of transformation this represents. That was the first way. In general, we can say that if you have been given the object or the vertices of any kind of object, be quadrilateral or a triangle, and you have been given the image vertices that has passed through a certain transformation T. To get that T, of which is equal to A, B, C, D, you need to pre-multiply it with the given object. You pre-multiply the object vertices with the image, with the transformation to get the image. And here, if you have been given these image vertices and object vertices, you can still get the transformation by pre-multiplying it, and either by plotting on a Cartesian plane or by working it out. And I can conclude by saying that is how a transformation or a matrix of any kind of transformation is found. Our next section, we shall pass through successive transformation. Under successive transformation, we can say we have seen what transformation is and what it does to a given object. Now, in successive transformation, it simply means you may be given several kinds of transformation being operated on a given object. And this object passes through all these series of transformation given to become a given image. For instance, having, let's say, our first transformation be a rotation in positive quarter turn. Our first transformation is a rotation in positive quarter turn, and another transformation y being, for example, let's say 0, 1, 1, 0. This is another one is a reflection. Now, you be given a triangle or any kind of object, may it be a rectangle, a square, or a trapezium or a parallelogram. I will take a triangle with the vertices A, B, C, having a matrix of 1, 4, 1, 1, and 3, 1. Now, you have been told or being given that find the image formed or the image of the triangle ABC through a successive transformation of x, y as being given here. Now, being given this one, it may be xy or other kind of, maybe 4, 3, 4, 5, it may be even 6, but here we have been given 2. In order to find the successive transformation of this triangle through these transformations x and y, we shall first perform, this is the first to be performed, y is firstly performed. Then x proceeds after y. What do I mean? I mean, given any kind of transformation, the inner transformation you have been given is the first one to be performed, and the outside, it will be the last. That means that if you want to transform this one through these two transformations, then it means we shall first subject A, B, C, triangle A, B, C, through a transformation Y. We subject triangle ABC through transformation Y, and we shall first find the first image, that is 0, 1, 1, 0, 1, 4, 1, 1, 3, 1, and we get the first image of the triangle A prime, B prime, C prime, B 0 multiplied by 1, 1 by 4, we get 4. The other one applies, that is 1, 1. And 1 multiplied by 4 by 0, you get 1, 1, 1. Ah, 1, 1, 3. Now we have found that if triangle ABC is passed through the first transformation y, we were told to transform it through xy, is passed through the transformation y, we shall get the first image being this. But we have been told to transform it through transformation xy. Now, our first transformation gave us this image. Now, we shall now transform our image through the second transformation. And that means that we shall now take triangle A prime, B prime, C prime through a transformation of, we shall take it through a transformation of now x, which is 0, -1, 1, 0. And we shall now get -1, -1, -3. And this is now A prime, A2 prime, B2 prime, and C2 prime. And this, if we need the coordinates of here, now it will be 1 by 4 and 0 by 1. 1, 4, it will be 4 plus 0, 4. 1 by 1 plus 0 by 1, we get 1. 1 by 3 plus 0, you get 1. And now we find that our final image, which is A2 prime, B2 prime, C2 prime, we get our final image being -1, -1, 4, -1, 1, -3, 1. And we can say that the triangle ABC with this kind of vertices has undergone through transformation xy to give an image of A2 prime, B2 prime, C2 prime. And now we can conclude that this image is the image of triangle ABC through a successive transformation of xy. In general, we can say that given any kind of transformation, it can be xyt or even 4 xytv, whereby x has been given as 1, 0, 0, 1, y can be given as 0, 1, 0, 0, 1, 1, 0, and t being 0, -1, 1, 0, and d and v, t, v being 1, 3, 0, 1. This can be just an example of the transformation you may be given. And then you are being told, find the image of a certain triangle or a given quadrilateral after passing through a transformation of xy t. This is a successive transformation. It will simply mean you find the transformation, you firstly perform the transformation of t on that given object, say triangle A, B, C, with the given vertices. You firstly perform t on it. Then after performing t, you perform as you go backward. You perform t first with the given transformation. Then after getting that image, you now again subject it to another transformation, which is y, with this transformational coordinates. And then after finding that one, you take the image, you transform it using the last transformation, which is x. Now, meaning that when you have been given this way, you firstly perform the outwards or the outside going inward. That is, you move from your right hand to your left hand. Then the final image will be given after performing the last transformation, which is x. Same applies to this or any kind of given transformation. That is what we call successive transformation. Performing the first transformation, then the other one in order from the right hand side to the left hand side. Now, in our previous session, we already seen in how we can perform our successive matrices or a successive transformation of a given triangle or a given quadrilateral or any given object, and we get the image through that successive transformation. And here we now need to see if we have been given different kinds of transformations, meaning that one or two or three transformations being given, and we need to transform them or perform them to a triangle or any kind of given figure. What can it result to? Now, for example, being given as x equals to -2, 0, 0, -2, and maybe our y equals to 0, 1, 1, 0. Now, let's say this is our two transformations. That is x and y. We have seen in our previous session how we can use them to transform a certain given object to a given figure. Now we need to figure out and find a single matrix that can represent both of them, the two of them, as one, and transform a given figure or a given object to find the same result as transforming each of them to that object. For instance, let's say we have been given a triangle with the vertices, a triangle with the vertices A as 1, 4, B as 1, 1, and C as 3, 1. Now, in our previous session, we saw how we can transform this triangle using this one. For example, if we have been told transform triangle ABC through a successive transformation XY, we have already done it in our previous session. And now here, we shall see how can we transform this triangle using a single matrix XY as single, and give the same image as transforming each of them on this triangle. Now, we shall find a single matrix of these two successive transformations. And now, having given this x and given y, we can find xy to be our t, where t stands for our single matrix in this case. Now, t will be obtained by taking the matrix of x multiplied by that of y. But in our previous session, we said if we are transforming one of them directly to triangle, we start from the right-hand side to the left. You start with this one and then this going the other way. But if you want to find the transformation, a single transformation, you will start this way, that is from the left-hand side, going to the right-hand side. Now, meaning that if we want a single transformation for both of them, we shall start with -2, 0, 0, -2, then 0, 1, 1, 0. If given this one, Now we can find T, which is a single matrix of transformation for two successive transformations in this case, as if you multiply here negative 2 by 0 plus 0 by 1, you get 0. And then negative 2 by 1 by plus 0 by 0, you get negative 2. 0 by 0 plus negative 2 by 1, you get negative 2. And 0 by 1 plus negative 2 by 0, you get 0. Now we found our T, which is a single matrix of transformation of the two successive transformations, in this case as this one. Now we can transform triangle ABC using this one and get the same result as transforming it through first this one, then this one. Now, when you subject 0, negative 2, negative 2, 0, to a triangle ABC, which can be written with a positional vector of 1, 4, 1, 1, and 3, 1, we shall find that the object, this is ABC, you shall find the image being as 0 by 1, and then plus negative 2 by 4, you get negative 8. 0 by 1, 2 by this, you get 0 by 1 plus negative 2 by 4, we get the first coordinate being negative 8, and then 0 by 1 plus negative 2 by 1, we get the second coordinate being negative 2. 0 by 3 plus negative 2 by 1, we shall get our third coordinate here being negative 2. Now the denominator coordinates, we shall find them by doing the same, by taking negative 2 by 1 plus 0 by 4, and we say this is negative 2. Negative 2 by 1 plus 0 plus 1 at 0 by 1, we shall get negative 2. Negative 2 by 3 plus 0 by 1, we shall get negative 6. And we have found that this transformation, which is a single matrix, we have found that it transformed this triangle ABC from this coordinate to an image. Let's say this is double prime because it has passed through two successive transformations, that is X and Y. We find this one. Now, as your homework or test, I will give you this way. Now transform this triangle ABC through the first transformation Y, then you do a succeeding transformation X and see if you shall get the same result. Thank you. Now we can generally say that given different kind of matrices, we can still find a single matrix of those transformation. For instance, if you have been given X, as we have seen that X is, our X was negative 2, 0, 0, negative 2, and Y being 0, 1, 1, 0, and let's say W, you have been given as 1, 0, 0, 1, and even let's say D being cos 30 or cos 0. Cos 0, negative sine 0, cos sine 0, cos 0. You will find that if you are being, this is none than 1, 0 like the other one. This one and this one is just the same, just confusion, but it will take you through the same, but the result will be different. But if given this one transformation, you can still make them as required. For example, you can be told, find a single matrix of transformation of X, Y, Y, W, or even D, W, Y, X. you can still find a single matrix of this one by multiplying this matrix. You start with the D, then W, then you perform that of Y, and then X. What do I mean? You start with the first one on the second, you multiply the first two, then the result you multiply by the third, then the result, and then with the fourth. What you will have found is now the single matrix of transformation. It doesn't matter how many matrices you have been given. Any can work together as the same as given this one. You start with this one to this, you take this, you multiply by this, and then you multiply this, the result of this one, by this, W. Now you will have found a single matrix of transformation. Now we shall see, we are going to pass through our fifth subtopic, that is inverse of transformation. And here we can see that if given any kind of transformation, you can still find the inverse of that transformation. In that, when you transform that object to a certain image, we can find a transformation which will map the same image back to the object. For instance, if you have, let's say, given a triangle ABC with the vertices ABC as 4, 1, 1, 4, not 4, 1, 1, 4 I mean, and then 1, 1, 1, 3, 3, 1. Given this one, we can transform it through a matrix X as -1, 0, 0, 1, and get an image. If you transform this triangle using the method I have shown you with this transformation, it will give you -1, -1, -3, 4, 1, 1. Now we can see that this is the image of the triangle ABC with the vertices A prime, B prime, C prime being given as below. Now we can say that here it is our matrix of transformation X. It has transformed this one back, it has transformed triangle ABC to image which is this one. Now we need a matrix which can transform this triangle A prime, B prime, C prime back to the original triangle ABC. And that matrix of transformation, it will be now our inverse, because it is transforming the image back to the object. Now let's see what kind of matrix that. You can find it through 2 ways or 3 ways. The first way of finding a matrix of transformation, if given, for example, X as this one, you can find X inverse by taking X. X inverse can be found by taking identity, or the X itself, X, this one, multiplied by its inverse, or the other way, which is X inverse multiplied by X. It should be giving you an identity matrix. What is an identity matrix? Identity matrix is none than the one which gives you 1, 0, 0, 1. And this one maps, identity matrix maps an object back to its original position. This is the first way. You can find an inverse of a matrix by this method, whereby you can now take X, which is -1, 0, 0, 1. You multiply by X, which we don't know, that is A, B, C, D, is the same as this one. Just taking this one backward and this one, you should get 1, 0, 0, 1 as an identity matrix. And if you perform this way, you shall get your value to be A This one will be negative a plus 0, which is that y is equals to 1, and meaning that our a will be negative 1, because if you multiply, you divide both sides by negative 1, you shall get our a being negative 1. And b, now to get the value of b here, you shall multiply this one with this one, and you shall get negative 1 by b plus 0d. So that is negative b is equal to 0. So meaning b is equal to 0. And now to find the value of c, as always, you take this 0 by a plus c is equals to 0. So our c equals to 0. And again, we take 0 by b plus 0 by 1 by d. We get our d being 1. Now we can say that we have found our a, b, c, d to be a equals to negative 1, b 0, c 0, d equals to 1. Now we can replace, in place of a, we put negative 1, b, we put 0, and c, we put 0, and d is 1. We can find that the inverse of this matrix here, negative 1, 0, 0, 1, it is giving us the same as itself. So meaning that if you transform this object from these vertices through a transformation x, it will give you an image of a prime, b prime with these coordinates. Now we have found the matrix of that one, x inverse is that one. Now that was our first way you can use to find the inverse of a transformation. The second method of finding the inverse of a transformation, it can be that if you have been given, for example, that let's say y equals to negative 2, 0, 0, negative 2, if given this one as your transformational matrix, you can still find the inverse of y by using the form 3 method by finding first the determinant, whereby the determinant is found by taking the leading diagonal or the main diagonal, then you subtract the other diagonal, whereby it will be negative 2 by negative 2, you get positive 4 minus 0 equals to what? 0. 0 by 0, you get 0. Negative 2 by negative 2, you get 4. So 4 minus 0, you get our determinant equals to 4. Now to find the inverse of y, it simply means you find first, you take 1 over the determinant, which we have found here, and then here, in the leading diagonal, you exchange. This leading diagonal, you exchange the values in the leading diagonal, and then the other diagonal, this one like 0, 0, if it is A or AB or AC, you only change the signs. If it is positive here, then here you put the other sign that is negative after changing the leading diagonal points. And if it is negative here, it will be positive. For instance, let's see what happens. In here, we have negative 2, 0, and we also have 0, negative 2 as our transformational matrix. Now the inverse, we have found the determinant to be 4. The inverse of this matrix will be 1 over the determinant, which is 1 over 4. Then, in the leading diagonal, we exchange. We shall find, if we exchange negative 2 to other, it will be negative 2. And negative 2 to other diagonal, we find it will be negative 2. But this one, it is still 0. Even if we introduce negative 0 and here negative 0, it will still remain 0. Now we find that that one shall remain that way. So taking a quarter multiplied by 4, you get a quarter by 4, you shall get, this one gives you negative a half, and the other way it will give you 0, and this one gives you 0, and this is negative a half. So we have seen, in case you have a transformation y, and any object being transformed using this one, it can be mapped back, or the image can be mapped back to its original. For example, if it is ABC triangle, it can be brought from this A prime, B prime, C prime under Y by, if you take this one, which is y negative 1, y raised to negative 1, this is a just inverse of y, which is our transformation. And if you take the inverse of our transformation, you multiply it by the image, which is A prime, B prime, C prime, we should get our triangle back, ABC. That is our second method of finding the inverse of our transformation. You just find the determinant. After finding the determinant, you take 1 over the determinant, and then the inverse, here you exchange the leading diagonal term variables. And then the other diagonal, you change the signs. After that one, you open the bracket and you find the inverse of your transformation. The third method is whereby you have been given the vertices of those objects and the image. For example, given a triangle ABC, and then you have been given the image, that is, let's say, A prime, B prime, C prime. I'm just using that one to represent the coordinates. Now, you can still map this one back. This one represents vertices, of which maybe it can be 1, 4, 1, 1, 3, 1. Let's say, for instance, negatives, and then this one can be 1, 4, 1, 1, 3, 1. You can still map this one back to this by an inverse of what mapped it back to that one. What do I mean? I mean this way. If the first triangle was passed through a certain transformation, we can still find an inverse of that transformation by mapping it, the image, back to the object. Whereby if you take T inverse, you multiply by the object at the image, it should give you the object vertices. Whereby, now for our instant here, we had a certain transformation. It mapped it from this object to this image. Now we can find another transformation which can map it back, and that one will be an inverse of the first transformation. If you take T inverse of this one, then it will automatically give you the object. Meaning that if you take A, B, C, D, let it be our transformation or our inverse transformation, you multiply it by the object, the image, which is negative 1, negative 1, 4, negative 1, 1, and negative 3, 1. It should give you our object, which is 1, 1, 3, 4, 1, 1. What you will be finding here as the values of A, B, C, D will just be the inverse of the original transformation. I will be helping you to pass through area, scale factor, and determinant as our sixth section. In form 2, we learned about how to find area, scale factor, and also how to find the determinant of a matrix in form 3. Now, we shall find area scale factor of our matrix, given a certain matrix, and then we see how the two relates, area scale factor and the determinant. In other way, to find the determinant of a matrix, we understood if given A, B, C, D, let's say this is our matrix M, we can find the area, the determinant of it by taking the leading diagonal, which is AD minus CB. This is how we said we can find the determinant of our matrix, abbreviated as det. Now, our area scale factor is simply taking the image area or area of the image over the object area. The image area, which is the area of the image formed after a certain object has gone through a certain transformation. And then the object area is that object's its own area. So if you divide the two, you will find area scale factor. And if you have a certain matrix, area scale factor is just as the same as taking the determinant of that matrix, determinant of certain matrix, but you find its absolute value. What do I mean by saying absolute value? Absolute value of any given number is equal to the number without, maybe let's say, taking the only positive sign. If, for example, a number is having a negative sign, for example, let's take -1. Its absolute value, it will be 1. And if a number is 2, its absolute value will still remain to be 2. The absolute value of any given number is just if the number has a negative sign, you drop the negativity of that sign and you take the positiveness of the number. For example, if it's -1, you drop the negative sign, then you take +1. If, for example, that is the determinant, then what you will be getting, that is our area scale factor. For instance, we can do a little practice on that by taking a matrix, for example, as -3, 0, -0, -3. That is our first matrix. And then we have another one like -1, 0, -1, 0, 3, 1. -2, 1, 1, 0, 1, 1. Then, for example, another one, let's say 2, 2, and 1, 3. Now, let's say these are our matrices, but we have been told, for example, a certain triangle, for example, let's say triangle AB, a triangle ABC with the vertices A being, our A is 3, 5, B 2, 1, and our final vertex C is 4, 1. For example, taking this one, we can see that from this, we can find the area of the object formed, area of object. If you draw this one on a Cartesian plane, of which here it is 1, then 5, this is 4. So meaning the height of the triangle, the vertices of A, B, C on a Cartesian plane, we shall get that our A, B, C give us a triangle of this kind. Whereby, if you need to know the units between this one, you take, this one is at 0.4, this one at 0.2. If you subtract, you will get the distance from here to here is 2 units. And the distance from the base, this is an isosceles triangle. So the distance from the base to height, it will be 1, and here is 5. So if you subtract, you get here, it will be 4 units. The in between, we have 4 units. So if we needed to get the area of this object, Now the area, it is always a half base times height. But it will be a half times our base here, it will be 2. Because from here to here is 2. But our height is from here to here, which we have found from 1 to 5, we have 4 units. So it will be by 4. And you get this one gives you 4 as unit, 4 square units. We get the area of the object being 4 square units, and that one we write there as 4. Now, area scale factor we can determine, and also area of the image first. Let's first determine the area of the image, area scale factor, and the determinant. Now we have found that if the object is having these vertices, that is triangle ABC with the vertices 3, 5, 2, 1 and 4, 1, we shall find that the area of the object will remain to be the same. That is 4, 4, 4, 4. But area of the image, it will change according to which transformation is the triangle being subjected to. If it will be subjected to this one, we can still find the area scale factor and then the image, whereby the area scale factor, it will be determined by taking the absolute value of the determinant, whereby now if we need to find the determinant of this one, we can get that negative 3 by negative 3, that is positive 9, subtract 0, you get the determinant is positive 9. So here it is positive 9. And here the determinant will be negative 1 by 1, you get negative 1 by 3, 3 by 0. If you subtract the 2, you get negative 1 minus 0, it will give you negative 1. And the other one is negative 2 by 1, you get negative 2, minus 1 by 1, you get negative 2 minus 1, you get negative 3. 2 by 3, you get 6, minus 1 by 2, you get negative 2, that is 6 minus 2, it will give you 4. Now we have found the determinant, and the area scale factor of the respective matrices, we shall find that it will be the area scale factor. We said area scale factor is equal to the absolute value of the determinant. And here our determinant for this case, for the first matrix, is 9. So the absolute value of 9 is still 9. I mean the absolute value of 9, where 9 is the determinant of the first matrix, is equal to 9. And that is our area scale factor. The absolute value of the second matrix, the determinant of the second matrix, which is negative 1, it will be equal to, that is here now, we shall find the negative 1, the absolute value of negative 1, and we get this one is equal to 1. And if we substitute here, we find that the area scale factor of the second matrix is 1. And here negative 3, if you do the same thing, you will find here is 3, and here it will give you positive 4. Area of the image, now to find the area of the image, we said earlier that area scale factor is obtained by taking the area of the image or image area divided by area of the object or object area. And for instance, the first one we have 4. So if we have 4, our 4 is the area of the object. To find the area of the image, we shall place there like letter X. For example, here our area scale factor for the first matrix, we have area scale factor being 9. Now, our area of the image we don't have. That is what we are looking for. Let's say, let it be X. Now our area of the object, area of the object we found for the triangle, the object is having 4 square units. If you do that way, you cross multiply, you will find that our x equals to, this one you will multiply by that, this is x equals to 4 by 9, you will get equals to 4 by 9, which is equal to 36 units, square units. So it's 36 square units. The same apply to the second one. You place, in place of 9, where there is area scale factor, you place 1. And then where it is area of the object remains constant, and that is 4, and you will find the area of the image here being 4 units. I will urge you to please continue filling the third and fourth using the same procedure as before.
We're going to see our next session is on shear and stretch, and we shall start with the shear. We need to see what happens when an object is submitted to a shear matrix. So we shall consider a given rectangle, for example, and let's say we have point Q at this point, and let's have another point here, M. And we see that if we transform it under a given matrix, you find out that it will have the same So we are going to see that if you transform it under a given matrix, you will find out that you will find an image of the first object being transformed as this we have here, which is A prime, B prime, C prime, and D prime, with the points which were Q and M being transformed to Q prime and M prime on the another figure or image which we have obtained here. So, as we can notice here, if this one was on a Cartesian plane, for example, if this one was on a Cartesian plane, you will identify that they all have the same height. This one rises up to 4, meaning its height is the object A, B, C, D is having height of AD, which is equivalent to 4 units. From the same figure, we can identify that as you see the image ABC, AB prime, A prime, B prime, C prime, D prime is having also height, is a parallelogram with a height of, actually, if you move that way, you will find the height is similar and the height is 4 units too. So the height of that one now will be determined by, you can take at any, you can transfer that one this, but you will understand that the height here, actually the height is also 4 units. So meaning, if both of them have the same height, and we can see they are sharing the same base here, that actually means if you find the area of ABC, D, which is our figure here, the area will be equal to the area of the image because they are sharing the same base. They are sharing the same base, at the same time they are having the same height. So the area of this rectangle here is the same as the area of the parallelogram, which we find is an image of what we have here. And as you see, the points move with respect to that, and as you can see, the line which is not parallel, this is the parallel line, DC is parallel to line AC, and we can see it has moved to D prime, C prime. But the lines which are not parallel are AD, which are not parallel to our x-axis or to our point here, AB, to line AB. That line which is not parallel to line AB Now, we have seen that it has intersected with the image actually intersected with the lines of the object. So meaning that lines which are not let me just say, which are not parallel. I will use this symbol to mean parallel to our invariant. Actually, this one is not variant, because if you view it well, you will find out that AB and A prime B prime are on the same line. So meaning that is the invariant line. So let's just say lines which are not parallel to our invariant line intersect with the object's lines, as you can witness. So meaning that those lines which are not parallel to our invariant line of the image now, these are the images now, that is A prime, we can say A prime, D prime, and B prime, C prime, intersect with what? The object line intersects with the object, as we can witness here. Therefore, from here, since we have said the invariant line doesn't vary, and also the area of these two figures, which is the image and an object, are the same, therefore a matrix which maps A, B, C, D, this object, to A prime, B prime, C prime, what we found here is what we call shear matrix. And therefore, if you want to describe a shear matrix, you will state the invariant line. The invariant line may be on the y-axis, maybe on the x-axis, or maybe at the middle, but it may be identified as the x or y line. So you have to state the invariant line. After stating the invariant line, you also state one of the point which is not on the invariant line and be vary from one point to another. For example, here, what I'm talking about, if I mention you state one of the point which is not on the invariant line, is like point D, which has been mapped to D prime, or C, which has been mapped to C prime. But those points which are on the invariant line, we see they are still mapped on the same invariant line, so meaning they are not variable. So this one are what I'm referring to line, the points which are not on the invariant line. Therefore, you also state a point which is not on the invariant line. For example, if we could describe this our shear here, we could now give out that this one is a shear matrix. It's a shear matrix actually. Let me just explain. It's a shear matrix with the x line invariant, and then I could have taken one of the point, either D or C, because they are the one which are mapped to the other. So you take one of the point. If it is D, you state its coordinate. Then you state the coordinates of the image, and you will have described a shear matrix fully. So let's see an example. Triangle AOB has vertices at O, which is 0, 0, B is 3, 0, and A is 3, 0, and B is 3, 4. So show on a diagram its image under shear whose matrix is 1, 0, 2, 1. Let's see. We have been told that we have a triangle AOB, and that triangle has coordinates 0, 0. For O, we have 0, 0. A, it is having 3, 0. And B is having, actually, is 3, 4. What we shall do, because we have been told the shear transform matrix here we have been given as 1, 0, 2, 1. So we need to find the image and state which we give out which kind, or we describe that transform, the transform of that shear fully. For example, we shall do this. In order to find the image of that triangle, we shall take the transform which we have, we multiply by the object coordinates, then we shall find the image coordinates. So for instance here, we have the shear transform here we have been given as 1, 2, 0, 1. We are going to multiply it by the object coordinates which we know. For the O, we have 0, 0. And then for the A, we have 3. A is 3, 0. And for the B, we have 3, 4. Therefore, if we do that, we are going to get the image coordinates. For instance, we shall have 0, 0 for O. If you do that way, you will find, if you multiply, you will get for the O, this should be capital O, not to look like 0. For O prime, you will have 0, 0. Here shall give you 3, 0. But the other one will vary, and it will vary to, if you multiply well, you will find you're going to have 11, and here 4. Now we have found object, we were given the object coordinates, and now we have found out the image of that object. So we can give this triangle on a Cartesian plane and be able to describe its transform. For example, we are going now to draw a Cartesian plane and map the points on it and see which kind of a transform took place. Now I'm going to plot the points of the first triangle, of which is our object here. I'm going to plot the points on the Cartesian plane and also plot the same points of the image on the same Cartesian plane and see which kind of transform took place. So for example, here we are going to plot, and I will find for 0, 0 here will be at that point for O. And then A will be 3, 0, so it will be at this point. Now that is for A. And for B is 3, 4, so it shall be somewhere here. So you will find out that the triangle resembles a right angle triangle, and this is our B. So that is the triangle, which was the object. Now we have to draw the image, and the image you will find that the first point is the same as the object's point, so it will remain here. That is O prime at that instant point. And then for A prime is the same here, which shall remain there. But for B prime, now change to 11, 11, 4 at this point, but it is at 11, 4. It is at that point. So if we draw that triangle, you are going to get out you will find out that this is now our B prime with the coordinates 11, 4. So as we can see here, our triangle AOAB has undergone shear matrix, and it has become this new triangle which we have O prime, B, A prime, and then B prime. This is the image and this is the object. From there we can see and describe that triangle, and we can say our triangle is the matrix or the shear matrix which we were provided with was that transformation took place with a shear matrix of x invariant. X line was invariant for that instant because we can see they are taking place on the x as the base, so it doesn't vary. X is invariant, and at the same time we have one point which is not on the invariant line but has mapped from B to B prime, so we shall say is x invariant with B prime, B of 3, 4 as its coordinate mapped onto, it has been mapped onto B prime which has 11, 4. And by that we shall have described that matrix because we can see it is in the x invariant, and one of the point map was from B, which was 3, 4 to B prime, which is 11, 4. The same can apply with the y invariant, and you only state the invariant line and one of the point which is not on the invariant line but varies from one point to another. So that is what you state and give out the coordinates of that point. Let's see how stretch matrix is also given out. In general, if you are being given a shear matrix, then it will be, if the x-axis is the invariant line, then if the x is the invariant, let me just give x is invariant line because it may not necessarily be x-axis. If it's the invariant line, then you will have 1, k, 0, then 1. This is the matrix or a shear matrix with x-axis invariant. Then if it is y-axis, y line invariant, or y as the invariant line, then the shear matrix which will be provided with now will be 1, 0, k, 1. These are the matrices which you may encounter, and if you find one of them represented in that form, then you know that one is a shear matrix. Let's see how we can find stretch. We shall see one of the objects in case we have this one here. And you find that this object has been extended in such a way that if this one was A, B, C, D, it has now extended to form A prime, B, D prime, B prime, and C prime. If you witness, you will find the points B has only moved perpendicular to point A, that is point B has moved perpendicular to point A, and also point C prime has moved perpendicular to point D, which is an extent of point C. With that, we can also see that ADCB can be taken as our object. And with that also you can find that the new image formed, you will find under given stretch matrix, you will find that the image of A, B, C, D is A prime, B prime, C prime, and then D prime. So with that, we can say this object has undergone under a given stretch matrix so that it looks like it is elongated from the original position. It only elongates with points perpendicular to the ones which are not varying. So for example, in this case, if you want to give out here, we want to describe this stretch here, you will say this is a stretch, and if you want to give it out, you will now state also the invariant line. For our case there, if this one was drawn to a scale or to a Cartesian plane, you will find that if this was a Cartesian plane, you will find out that this one was to be y invariant at this. We don't know at this point what that one is at. So you will have found out that this one was at y invariant. The invariant line was y, but the points also moved with a given scale factor. And if you want to find that scale factor, you will take the image which moved, that distance of the image, then you divide by the original, that for the object, you will have find the scale factor. For instance, for this image here, this diagram which is here, if you want to find out the stretch scale factor here, you will take A, B prime, A prime, B prime, and A prime is the point of the new image formed, which is the image. Now it will be A prime, B prime, which are the points of the image which formed. Then you divide by the original, which is AB. And if you find, whatever you will be finding here is what we call scale factor. And actually, it should be the same as the other line which varied. For example, here will be D prime, C prime over DC, which was the original lines. And if you do that, we have said this is what we refer to scale factor. If you have been given any kind of a matrix and if you draw it down, then you should state the line which is invariant and also state the scale factor. For example, if given this point here, and we have been told, for example, this one, let's say it is at, we can extend this line and give it an example. Let's say I have a unit square here, or a unit square actually, with the points A, B, C, D as given below. So this one, let's say, after undergoing a given stretch matrix, you will find that it moves up to, for example, up to 4. Then if I want to describe what kind of a matrix took place, I will say this is a stretch matrix. It's a stretch matrix with, as I can see here, is the X line, then the Y line actually is the Y line which is invariant. So I will say it's a stretch matrix with Y line invariant. And you give out the scale factor of what occurred. For example, there I will go to give out the scale factor, and I have given you how you can calculate the scale factor. For this instance, we shall find the points which varied. For example, here we have B prime, here is C prime. So the points which varied is B varied from B to B prime, but A and A prime of the points remains the same. So we shall have, if we need the scale factor, we shall take A prime, B prime, which we have is from this point to that. So as we can see, actually from this point to there, so it shall be the same as the denominator, so that is 4. It has moved with the 4 points, so it shall be 4 over the original, which is 1 point at the same which is there, because if we witnessed here, it's just 4, 1. It's just 4, 1. So if we take the invariant, we are going to take what occurred in the X. So we shall get 4 divided by the original point, which is from here to here, or the same from here to here, which is 1. So we shall find out that it has moved with a scale factor of 4. So we shall say with a scale factor of 4. So our unit circle underwent a stretch matrix with the y line invariant and with a scale factor 4. So if you want to describe a matrix of stretch, you give the invariant line and you also state the scale factor. And if the scale factor is not provided, you have seen how you can calculate from the image and object which have been formed. So in general, if you want to identify a stretch matrix, in case you have X line invariant, X as the invariant line, then you will find your matrix will be in position of K, 0, 0, then 1. If you find a matrix which resembles that one, you know that one is a matrix with the X line invariant, but with the scale factor K. That is the scale factor there. And for the other one, if Y line is the invariant line, let's just say invariant, you will find out that you will have the opposite of that, which is 0, 0, 0. Then actually here should be 1 because that is the one which will be stated. So it's 1, 0, 0, K. If you find this way, you understand that is a stretch matrix with Y line invariant and has a scale factor K. With that, we have come to the end of shear and stretch matrix.